Are you ready?
Yes.
So, yes, so this what this does is that it allows you to count the number of like operations in your, so like if you do one field element plus another field element, that's one addition, right? So it will count those metrics for you. That way everybody will be able to compare their implementations on an even playing field rather than time based where your CPU might affect things. It's not like on an equal. So let me add it first. How do we add this thing again? It's not hard. Like it won't take long. Yeah, me and Francis.
How do you get the link?
Let me first make it work, then I'll send it to you. I can't remember if this works. Aquax might have updated their packages. Oh. I don't know what causes this. 'Cause I do have internet, but then it thinks I do not. Okay, so we have the package now, right? So to use it, this is how you use it. So what we're doing now is that we're wrapping your field element. We're wrapping it. And then that wrapper would do what the field can do, plus some extra stuff, right? So let's look at this sum check that we did now. What I could do is I could wrap this FR in something else, right? So I think FT. Can't remember. So you can do like a type. Let me just try something. Okay. So what I've done now is that I'm wrapping that FR in something that will give it like extra powers. So instead of, let me just name this as like arc field. Then let me use FR is equal to arc field. So I don't have to change my code so that it's still FR. So now this should be all, right? So I think you just call like start tscope and then you do whatever you want to do. So let's say you want to prove. Then you can do like end tscope. What does this take in again? So this is like sum check. Let's just call it sum check. The end tscope.
It's just any name.
Yeah, any name.
Why are you putting it under the verifier?
I want to just benchmark prove.
Print summary, is it part of the package?
Yeah, it's part of the package. So it's just like print a summary of all the distance. So now if I run test sum check, okay, so this FR, this should have worked though. I think there's a, yeah, I think there's a limb stuff. Was there a fix for this? Are we supposed to pass two things? In FT, right? Are you sure? We're calculating the lane by ourselves here. What we're thinking is that let me check my code. It might just be like they have updated something, potentially. So this is what we did just now, right? We did FT, FR, and then we now have like bench. Yeah, it should just work like that. So I'm thinking that it's probably that they have updated something that is no longer aligning. But let me show you what it's supposed to look like. Then we'll fix it and then you guys can now like try it on your own.
The way your directory structure, you have 2023, 2024. So you track what you do for each year.
I track what I do for each year. So I'm running benchmark. This is what time benchmarks look like. Right? So it tells you how long it took, which is like 1.7 microseconds. But then this is the range of so it runs the test multiple times. And then it tells you like the range, yeah. So this is like the average. And then it tells you like the percentage variance. And then it also compares it with your previous performance. So let's say you run it with a slow algorithm, then you updated the algorithm and then you run it again. Then you'll see that this percentage this thing is going to be higher. So like I haven't changed the code, but now see this one is supposed to be like 2% worse than before. But nothing changed. It's just my computer feels like being slower a bit now than last time. So that's why performance is very, very iffy. The higher time change, the worse it is. You'll see it in red. Like see now. They're saying it's regressed. Like it's 4% slower than it was before, but nothing has changed.
Windows
See this one now. There's a 10% improvement. What changed? Nothing. Then this is what the summary is supposed to look like, right? So it's telling me the number of additions I'm doing. I'm doing 3.9 million additions, and then 11.7 million subtractions, and then 7.8 million multiplications in total. So that's what I don't know why it's not working right now.
How is this one? How did you get it?
Huh?
How is this? Not
How?
exact. No, this is not normal bench there. This is part of this one. This is your package working.
Yes.
The benching was the time.
Yes.
Your package. How did you
Build it.
like what's it doing like?
So what it's doing is that it is wrapping the field elements in a so it's like number 2 now. Rather than just number 2 as number 2, we now put something around 2. So that thing is going to act like 2. So if you take that thing and another one of it, so 2, 2, and then you do a multiplication, it will give you 4, but wrapped 4. It's okay, like it's a wrapped number. But then whenever you do an operation, it's going to track that you did that operation. So when you now say print summary, it's now going to like print out everything that it has tracked so far. So that way you can now use it in your different implementations, and then you should be able to see how many ops you did. And that one is independent of how fast your PC is. You get?
This code you run, I do like everything. Why do we have so much complication?
This is like.
But at the end, we do some
This
stuff.
addition of multiplication.
At the end, we do
You said?
Okay, this is not an.
Yeah. This is the polynomials are big. So this is like no. So this one now is like a global summary, but this one is specifically for 18 variables. For 18 variables, it's doing like 524 and then 262. Yeah. So this is like evaluate. You create a 2 to the 18. That's like 262k evaluation points in your multilinear poly. Then you now evaluate it at 18 random assignments for the 18 variables. Yes. Yes. The 2 to the. You'll see the benchmark.
How did you generate it?
Hmm?
How did you generate it?
See, so I have this thing called endpoint, right? It takes the number of evaluation points that you want, and then it sets up like a rand. So it's just like creating one random element up to n. So what we'll do is we'll send another video, the part 2, that shows you how you can do the benchmarks. Then it will be shorter.
But now, how do we? Your question is very
Oh, somebody should also ask.
What is that?
So what's the question now? So that
I did like two night callers. End the call. No, you end the call.
let's figure out why it's not working. So no question. No, I'm talking about Casa.
Who don't do the video? What made you want to pay? What made you want to pay? Everybody weekend. All of you are waiting for who will ask this question. You
Okay,
can
we
wait.
build the car. Okay, is it that, okay, I think the question wanted, like,
Oh,
is it going to work on Windows?
Is that?
ah.
Will it work on Windows?
Yeah.
Yes, sir. Anywhere Rust works. It's Rust.
Yeah, my own question is like, how do we decipher how fast it is from just the summary? Like, what do we, like, if I see your summary and my summary now, like, what am I using to say, oh,
So additions
it's faster?
additions are cheaper than
Yes.
multiplications. So if someone is doing more multiplications, you should automatically know that person is most likely slower.
So what if, in the case of like, me having more additions than someone and lesser multiplications, but
Yeah.
then I have probably like an inverse operation, and that
That's
person
bad.
has a lot of multiplications
Yes.
and some
So
additions, but no.
Usually you're supposed to combine the time and this
Okay.
also.
Okay.
Like when we did one, right, we realized that we have inverse. Then we now looked at arcworks also, and realized that inverse was 0.
So,
And that inverse is really expensive. But we were able to now see like, oh, our cost is coming from the fact that we're using inverses. Then we now dedicated our efforts to figuring out how to get rid of.
so it's sort of a guide.
It's kinda
to
like a
know
guide,
what
exactly.
So which one is inverse?
Like he did it now in Lagrange, f.inverse to unwrap. That's really expensive.
I have an idea. What is there a way you can incorporate AI into this that at the end just use its AI power to give you like a summary, like telling you, okay, this is like, you know, we can,
Like this is what that
you know,
I don't know. I mean, like, what would the summary look like, for example? What would the summary look like?
like a human readable, like English summary.
It's possible. I think it's possible.
Like, tells you, okay, with this can be this.
But we even had like, so there's polynomial, right? The one that you guys know is just Boolean hypercube, 0, 1. But then you could have 0, 1, 2, 0, 1, 3, on and on like that. Yes. The thing now we're looking at is like, sometimes it might be cheaper to do certain things in a higher, not a higher dimension, or not really dimension, higher HC. We call it HC. HC, hypercube. Like 2 HC is like Boolean hypercube. Then 3 HC is like ternary hypercube and on and on like that. So we're now looking at this situation whereby you can have a polynomial that can kind of like morph, right? So you might have data that was defined in 2HC, but then you want to do an operation that is better in 3HC. So it will just like morph itself to a 3HC polynomial and then do that operation there. And then you can just like move on and on like that. Then now combining that with like reinforcement learning in terms of AI. So now kind of like, there's something called the beta lesson in AI, which is that general algorithms win in the long run because of compute is increasing exponentially as we're having access to more and more compute every year. So if you're trying to make, let's say, something that can beat a game, let's say Go or something, there's a way you could do it whereby you would take all human knowledge and try and like encode it into a model. That's a very specific algorithm, right? It's specific to Go. That algorithm does not scale with compute. So as compute is increasing, it's not taking advantage of that compute, but it gets like a really good head start. So it gets a really good head start, but then it gets like flatlined. That's like, it's capped. The growth is capped. But then the more general the algorithm is, the more it can harness compute. But also the longer it takes before it can start seeing something that can, let's say, play Go properly. So like DeepMind, that's an AI company. They have AlphaGo, but then they have two variants of AlphaGo. There's AlphaGo and there's AlphaZero. AlphaGo first of all started learning by looking at expert games, so expert Go players, and decided to try and model how they play the game, and then it now went from there. So it got that head start immediately and it was able to like start playing something useful. But then it got capped. So like let's say maximum rating. Then there's now AlphaZero. They didn't even tell it, like they didn't tell anything, they didn't show it any human game, nothing. They just said search and then they set the rewards. That's reinforcement learning. So it just kept on going like that and then it surpassed AlphaGo. I think it's like it just can't lose to AlphaGo. So that human knowledge kind of like capped the way it can harness compute. So the beta lesson is now like, this thing has happened so many times. And you know why researchers, they really love to like find something really cool and then encode it as like a program. But then these guys are now saying that those things are not useful. Like all those Go researchers that are like, oh, I found a pattern in how humans play Go and I'm going to like implement that. That's why they call it the beta lesson. Like you don't actually need that. Like if you have a general algorithm that has the right incentives, it will find that thing that you're trying to find by itself, but it might take a longer time. So it's usually like a graph whereby the one that you input the knowledge might have a head start, but then this one might be here, but then at some point in time it just like surpasses. So that's the beta lesson. So now like, can you apply the beta lesson to more than just let's say, AI systems. Like this ZK now was kind of like doing research, trying to find like things and that are smart, and then we're using that. Is it possible that you could also do something like that, where you create a very general system, and then you apply search to that system? So rather than trying to find something great, you let the computer find something great with a lot of like compute. Yeah.
So like this same thing like actually came to my mind from some few days back. So I was thinking about like doing something in a faster way. So I actually found out something like you know there's something called like Higgs law. So it's like the longer you have suggestions, the more suggestions you have, the longer your decision making takes time. Like
What are my suggestions?
okay, the more options you have, the longer your decision takes time. So Google kind of uses it for their search engine.
Okay.
That's why they show you better options so that you can quickly make a decision.
Okay.
Then UI UX engineers also use that.
Okay.
So apart from UX or whatever, so what about in a system like what we were talking about, whereby the fewer options you have, the faster your decision making will be? How will it apply?
So in this case, what are the options?
That's the thing.
Oh, okay.
That's what I'm trying to figure out.
Alright, go ahead. Yeah.
So,
Wait, I'm coming.
what's general? I'm thinking of what's general in benchmarking, whereby, because let's say you're testing, let's say you're testing your code, and you're benchmarking your code, testing like benchmarking your code, and someone else is benchmarking their code in different pieces, right? And you know, you have to go through the process of checking the summary and comparing them. So I was thinking, is there a way all these things can be converted to
A number,
bytes, to bytes, like
right? A signal.
yeah, a size of bytes. Like while you're benchmarking, you're converting them to. So at the end of the day, if you're done benchmarking your code, it will tell you the size in MB or kilobyte and it took to run this code, and it tells you like the size in kilobytes and MB that it took to run that other person's code. So it becomes a general parameter all across everywhere, which you can just look at it and you say, okay, this runs with this byte, this runs with this byte. So that way, you know, you might not necessarily need to start, you know, looking at the summary line by line before you like.
Time is a good proxy for that, right? But it's dependent on CP, with PC. But you can also like set, so maybe through benchmarks, you can figure out like exactly how much each operation costs relative to one another. So like maybe one addition is supposed to be like, one multiplication is like 5 additions. So you have this relative benchmark on the up level. Then you can just like use that to get like a relative time. That's not like based on the system.
I'm just suggesting so the two can have versions.
Yeah.
Yeah, so my own question.
Okay.
The first one was your library.
Yeah.
Are you like doing a straight implementation or something like that?
Yes. Yeah, we're doing an implementation on the field. So FT, right?
Yeah.
It holds the field element inside, which is something that implements prime field. But then all we do is that we also implement prime field for FT. So here. So now, see, when we're doing something like add now, right? So we do the regular add with the inners, but then we also call this. So update add. There's like a global add count, more count, sub count. So we'll do the operation, and we'll wrap it in FT again, but then we'll count it.
Okay. So for the second one, you said you were talking about inverse. You said it was in Lagrange, you did inverse.
Yeah, for example, Lagrange, you know, we're doing inverse.
Where it was, okay, whatever. What I
Scalar
did
division.
was,
Like division,
Right,
exactly.
Scalar division.
Yeah.
what I did was power minus 1.
The power minus 1 for what?
Lagrange.
Inverse Lagrange.
Yeah.
So you know there's a numerator and there's a
No, I
denominator,
didn't
right?
divide, so just did times.
Power raised to
Two
power
raised to
minus
power
1.
minus 1.
That's the inverse.
It is still convert.
It's still inverse. I don't know whether
No, like,
it's...
I know you do normal inverse. But
Yeah,
like,
I don't know which one is faster.
that's what I'm saying.
That seems expensive.
So if
I don't know which one is faster, but you have to measure it. Maybe like criterion or something.
if inverse is expensive, then why is FFT cheap? Because you are performing inverse there too.
That's for IFFT. But that's just once.
Huh?
But that's just once.
Yeah, but even
How
I think-
your implementation, does it convert inverse every single time? Just the top, right?
What's the high
The root of unity. Huh?
What's the high there?
I is inverse FFT.
The inverse first one.
Yeah. So but FFT is like n log n
Yes.
versus n square. N log n is already better than n
Yeah, I
square
get that one.
for large values of n.
Then what of IFFT? That's an inverse now.
Just one inverse. It will
Just for the root of unity.
it will be diluted. Yeah.
How do you measure the cost of an operation?
You use a micro benchmark, like criterion.
No, like when you say
Power.
addition is cheaper than multiplication, what is it like? You know we have gas in solidity that this contract is cheaper than this. So what's that unique operation?
So on a like physical level,
Yeah.
every line gets compiled down to assembly
Okay.
opcodes. So let's say saying something is cheaper means that it converts to less opcodes than the other one. So we're saying technically that multiplication gets converted to more opcodes than addition gets converted to. But to actually get that, you can use like a benchmark that just does addition, and can use another one that just does multiplication and see the time difference. But then there's another tool called code bulk.
PC dependent.
Before you, there's what I'm driving.
Is what PC dependent? Sorry.
What you say is like CPU dependent based on.
Yeah, different CPUs might convert to different like opcodes.
Okay.
So there's a place I'm driving at. So,
Yeah.
You know, I'm still going to form. So the way operation works on the ABM, like the
Yeah.
stack machine, where there's a point number of variables you get stack with it if it's up to 16 and it's measured in bytes. So from that code you showed now, where you update something and get the number of counts of like the count of addition, subtraction, and all of that. So I was thinking if maybe you can get the unit of the cost of an operation. For instance, for addition, you get the unit, like what it costs, general cost of addition, subtraction, and all of that. So now, same way you're counting, tracking the count of operations. Now, when you see addition, you increase it by
Multiplies by the count.
by that size. So that way, at the end of everything,
You have a time.
you have like a size, a byte size of the general benchmarking.
Why are you calling byte size?
So I'm just assuming that byte is the unit of your costing. So if maybe addition costs 2 bytes, or
You know that byte is like
sorry, let's forget about bytes. Let's say addition costs one int. Like
Byte.
multiplication costs 3.
Yeah.
So you have
You are
something
trying to like normalize everything into just one
so that
thing,
way it won't be dependent on PC now.
and it will still be a single number.
Yeah, it will still be a single number. So you can run your benchmarking on your code in your system. I run it in my system.
And to
but
still be.
what we get will still be used.
You can still
to
measure.
generalize. Yes.
Maybe it's just saying maybe
Like
assign You can assign a number to
Yeah.
Yes. So because
Exactly.
that way now you won't use time again, because time now is dependent on CPU. You're
Yeah.
using the operation
Yeah.
to benchmark it. So
Yeah.
at the end
Your goal basically is that global summary.
Yeah.
One number.
So,
Yeah.
yeah.
So everybody can just say,
It will be
Run
like
your
bench
code, I
score.
run my code.
I am
you
54,
check.
Exactly.
and you are 92.
Exactly.
Yeah. But the problem with this now is that we face like a really big bug when it comes to concurrency. So let's say you are doing 500 operations. You might be doing it on a single core. 500 operations on a single core. But you might be doing 500 operations on 10 cores. So that 500 has been split into 50, 50, 50, 50, 50. So the actual time to take is just 50. Right? Because they are all doing it in parallel. But the guy that is doing it on a single core is going to take times 10. It's going to be 10x slower than the other guy that is doing it in parallel. But when you just look at the operations, it's still just doing 500 operations. They're both still doing 500 operations. So what we're trying to do is figure out a way to incorporate concurrency, where we will be able to tell you the number of feed operations per core. When we can do that, then we can now, but we have not been able to figure out how to do that. That's like a really hard problem. But if we can figure out to do that, then sky is the limit. Because now you have like an alternative way to bench that is like system agnostic, which would be really cool. But we'll figure it out one way or the other. Alright now. Any other? We're good. So we'll check that thing out and then we'll send it over the weekend or today. Then, but we can still do that right now. For like some check GK or everything, nobody's doing parallel stuff. So we can still get like a number based on like relative. In fact, there's something called procedural macros in Rust. So it is even possible that as your procedural macros, as you're compiling your Rust code, it will go and find out like on your. No, there's no what it's. And I said like on your system, it's going to figure out like how long addition takes on your own system, how long multiplication takes. But then it's no longer a general number anymore, so it doesn't work. So you just figure out like a general number for addition, multiplication, division, inverse, all those things. They just use that same number for like every. You can make it to be. Is it like ratios?
Yeah, something like that.
Maybe, yeah, that might work.
Whatever it is.
Or it might not.
The 2 will be a global 2.
Of course. Of course. Alright now. Let's end here.